Good afternoon, everyone. This is Geraldine with Infrastructure Resources, and I would like to thank you for joining us today for our webinar, Processing and Integration of High-Speed 3D GPR Array Data, a robust tool for the future ASCE 38 3D standard for subsurface utility engineering with Matthew Wolf. Matthew is president of ImpulseRadar USA Incorporated, where he is directly involved in all aspects of managing operations in North and South America. Matthew has extensive experience in the development and implementation of GPR and other sensor technology for subsurface investigations. Over the course of his career, he's provided consulting services for the SUE industry and has broad experience with geophysical methods for geologic, geotechnical, environmental, and infrastructure projects. Mr. Wolf has published several articles and has presented at numerous conferences. He is a member of the American Society of Civil Engineers, Utility Engineering and Surveying Institute, and chaired the NOLCA GPR National Training Standards Committee. Today's webinar is sponsored by ImpulseRadar, one of the world's fastest growing ground penetrating radar technology companies, focusing on combining experience with state-of-the-art technology to develop user-friendly GPR instruments. To learn more about ImpulseRadar, visit ImpulseRadarGPR.com. To ask a question during today's webinar, just click on the Q&A icon in your Zoom menu and type in your question. Matthew will respond to questions at the end of the webinar. And with that, Matthew, welcome. Thank you for joining us today. I'll turn the screen over to you now.
Okay, great. Thank you, Geraldine. So I'm going to share a screen now, right?
Yep.
Okay. And we are going to do this. Okay, am I shared now?
Not yet.
Okay. How about now?
Yep.
Okay, good.
You just need to go to the...
Yeah, here we go.
Perfect.
All right, great. Hey, thank you, Geraldine, and thank you, Eric, for giving me the opportunity to do this. You have an excellent team there. It's an excellent publication. I've been very involved with your publication for many, many years, probably since its infancy. When it first became published, a publication focused on utility industry. And I want to say, hey, to quite a few people I know that are out there that are either existing customers or I've worked with the industry for many, many years. Hello to everybody, and I hope everybody is well. What I want to do today was, essentially what the goal was today was just kind of introduce the software that we've developed. The Raptor arrays been out for quite a few years now. We're the first company to break the speed barrier in terms of getting high-speed data from a radar array. And I'll explain a little bit about the tech on that, which others are catching up with as we speak today. And then I'll just do a little introduction on first with our product line, go into a little bit of the technical details and why we can go so fast and how it works. And then we can go into, let's say, the operations in the field. I'll show a quick video, and then we'll go ahead and watch data be processed, and then I'll kind of work that into the 3820 standard that's coming out at the end of the year, and I'll spend more time on that at the end of the presentation, just to kind of make it go full circle. So in terms of who we are, we're not new. We've celebrated a 5-year anniversary. We've got quite a product line. We more or less started with the Raptor high-speed array, and then we've worked this technology into all of our products, low-frequency antennas for geologic investigations and stuff that's not really something a supervisor would get involved with in mining, geotech, and geologic for the most part, although some companies have a lot of range of services that may use all of these tools. And last year, I love the utility industry. I love the people. I love the dynamic of it. It moves fast. Last year, we introduced the Pinpointer GPR. It was the first wireless dual frequency antenna system. We all know why radar is important for the utility industry. Proud to say I was working in this industry before there were systems that were so easy to use and not so cumbersome. We know that they are essential and at this point in the process for both, everyday utility locating and the SUE investigations. So we released last year this pinpointer, and the main advantages of the pinpointer were really the simplicity of it. It's a wireless Android interface, and we're introducing something new now that is novel, and this is really coming from our customer base to add to the Android app, which we now call Viewpoint. And what we've done now for everyday use is integrate marker functionality with real-time. I want to use the term mapping loosely because I know there's a gentleman listening knows that we can't map unless we have a PLS, and we'll talk about that a little bit at the end of the presentation because it's relevant to the Raptor and the SUE industry for sure. But we have a moving map now integrated with our Viewpoint app, and it's really fantastic, and it's really geared toward let's say field sketching. We found a tremendous need both in one-call folks and also folks in the SUE industry that just want some kind of field sketch representation. Although all the ground will be marked out, survey will come in, pick those marks up. It's nice to have something you can record with the pinpointer. And I want to mention one more thing. The pinpointer actually has a built-in GPS system. It's actually very good. I'm not sure. On some days, I know I see up to at least 12 satellites. And on many days with wide open sky, we're actually sub-meter on most average days, which is adequate for a field sketch. So and you can also integrate an RTK system with it if you want to get down to, actually map and survey grade. We have some post-processing software. If you run different grids and different, let's say, more robust investigation of an area, you can use this software. But quite honestly, with the built-in mapping software, this will not be used as much because you're doing it on the fly. But it's still a robust processing software if you want to do multiple grid lines and so forth. So getting back into the, let's say, the array versus single channel, there's obviously conditions that the single channel 2D system will always be used. And there'll be situations where the Raptor array will be, or an array will be more sufficient or most efficient. And obviously the advantages of a 2D system is it can be used every day, anywhere. There's no restrictions on, let's say, space and so forth, sidewalks, behind buildings, over a fence, et cetera. And it's used heavily now in conjunction, adjunct to an EM locator. And we all know why we used to use GPR, so I won't rehash that. But maybe I should just briefly, if there's some new people here. We're going to find the terracotta, PVC, concrete, non-conductive materials that you can find, cannot find, with the EM locator. So when we talk about arrays, we're not talking about also small restricted areas that we're going to use it on. It's going to be used to its advantage. And the advantage is we're going to collect a lot of data. We're not going to be in the street walking around back and forth. And we are going to be able to produce 3D deliverables. And you're going to get a much higher density data than you'll ever get and try to achieve with a 2D system. It's not even worth trying to see how you can align those two, because we are doing tomography anyway, which is not something you can do with a 2D radar system. So anyway, so it's an imaging tool. That's the advantages versus a markout tool, if you want to summarize both of these columns. I just want to, for those that don't know, I mean, when we transmit signal from a GPR system, we have a transmitter, we have a receiver, and then we look at our standard hyperbolas, and we'll go ahead and back up, and we'll go ahead and do our markouts at the center point, let's say, of the hyperbola. And there's a lot more to this in terms of whether you're actually orthogonal, perpendicular to it, and these kind of things. I won't go into that. This is not a class on GPR, but this is the basic layout of how we get transmitted energy in the ground, and we get a reflection, we get your standard hyperbola. When you get into arrays, it's a little bit different. And there's different configurations. Everybody has a different way to do it, but one of the things we found to be the most efficient is what we call a herringbone pattern. And these antennas are actually inline polarization. They're actually set up 90 degrees to the standard 2D system. And there was a lot of research put in that many years ago. My colleagues in Impulse actually and myself were some of the founders in the very early beginnings of the first array ever developed in the world. And we worked quite hard on that. And there was a lot of research put into that with collaboration with others to determine this was the best configuration. And so we get both polarizations, as we call it, as we go down the road. So there's no need for a whole nother row of antennas to add weight and so forth and complexity of the system. And there's been a lot of testing on this. And the proof is in the pudding. As we go down the road, we see pipes and utilities in both directions quite clearly. That would be pretty obvious if we did not. So the nice thing about when we get into tomography, these are very modular also. The antenna positions are adjustable. We can do different configurations. Matter of fact, the Raptor array is basically sold as an antenna kit, and you can and add or subtract channels as you wish. And we're up to, I believe now, and I know our probably head of R&D is listening, Bernd Johansson, a good friend of mine. I may get this wrong, but we may be up to 56 channels now with our or even beyond that with our 800 megahertz antenna. So this is a very, very big array. Why is this? What happened? I mean, years ago, we were doing 4 or 5 miles an hour with a John Deere tractor. And all of a sudden, an ImpulseRadar, we're driving down the road at 50 miles an hour. And I'll never forget my first day with this thing as a pilot study in California. I was driving down a 50-mile-an-hour zone, and I was watching the data come out, and I still couldn't believe I was watching actually hyperbolas go by the screen as if I was walking. And so what happened? And I think it's important to explain a little bit. There's probably some very technical people on here that may or may not know. Some may know. Here's an example of the old array technology from a very long time ago. What happened was we went from a digital world where we had to build a trace, which is when we talk about radar and it pulses, we collect a trace. So we have this A scan, which is all the way to the far right. You can see we build this trace of, let's call it a trace that we build with 512 samples. In the past, what we had to do is these systems pulse at 100,000 times a second, or 100 kilohertz PRF. So there's a little bit of a misnomer on some. It is simple to look at it this way, but when you push the radar system and we set, let's say, a trace interval every 5 centimeters, or every inch, whatever units you're using, we have to build that trace. And in the past, to build it, we had to take, if we're doing 512 samples, to build this entire digital waveform of the received energy, we had to have 512 pulses just to build that one pulse. And this was called a ramp, the way that we time discretized the pulse and collected a sample to build this trace. So it worked, it was great, not too bad. And even with this type of system and the old systems, you could stack the data, and I'll explain stacking in just a second, because it really is much more robust with the real-time sampling. So we went from that, and we're still at 100 kilohertz PRF because that's an FCC ceiling on how much we can pulse these systems. But what we did now, and I'm proud to say our team was the first to do it at the frequency range for utilities, former colleagues that are all now at Impulse. We found a way and some technology with the ADCs, the analog digital converters, with the FPGA controllers, and I have some just very smart electrical engineers who can explain exactly how that works. I'm a geophysicist. But we have the signal come in through the ADC and the FPGA, and in a simple way to explain it, we digitize the waveform almost instantaneously. And that was unheard of. So now we go from having to build the 512 samples and 512 pulses. To do that, we have one pulse, one waveform digitized. And the beautiful thing about this is that we can stack, and we can do a lot of different things now. We have time. The system is not stressed like it was. So one of the most important things we can do is stack. And for those who are not familiar with that I'm going to give it the simplest explanation. It still goes back to where the term came from, and it's from the seismic refraction reflection industry. So there's a method we call in seismics where we can actually take a sledgehammer and pound a steel plate on the ground, generate acoustic energy through the ground, And that wave will go out and refract or reflect off underground structures and be recorded at a geophone downrange somewhere. And that's called seismic exploration. And if you've ever done it, like I have, you've got a 10-pound sledge, and you don't just hit it once. You'll hit this thing probably 12, 16, 18 times. And the reason you're going to do that is because the geophone is going to keep recording this over and over and over again. And the reason is the more of the signal that you put in that you want, the less impact the signals that are spurious, like the wind noise on the grass or a car going by, they're almost irrelevant the more we do this. And it's the same with GPR. If we can stack these data, these traces, hundreds of times, external noise gets reduced almost to nothing. And this is what really the quantum leap was with real-time sampling, was speed, and it was actually noise rejection. This looks a little complicated. It's really not. That bell curve is basically a representation of all the frequency on the bottom is about 250 to 750 megahertz is what this is. The center frequency, if you go put a line straight down the center, which I could have done in a presentation, is this what we call a center frequency antenna. The orange line is just it's kind of a cartoon to represent the old way of collecting a sample and getting the data into a trace waveform. And you can see it's kind of way up on the curve. But if you lower the noise, almost irrelevant, you can lower that down to the green line. And there's two things that the most important thing you're going to see there is we're going to increase the dynamic range of the system. And we're also going to increase the, let's say, the frequency bandwidth. If you can see where that green line intersects the purple, it's much wider on the bottom than it is at the top. So the beautiful thing about this is, and I've seen this in the early days, the real-time sampling testing, I couldn't believe it. I've been looking at radar longer than I'd like to admit, and I could see the high frequencies in the near surface, and the resolution was beautiful. But as you went down and down and deeper and deeper and deeper, the Earth rejected and filtered out the high frequencies, and all of a sudden you looked like you had two whole different antennas. So the advantages were great. We had more bandwidth, which means more information, which means better data and less noisy data. And particularly for use in the utility industry, it's extremely important because we don't work in very clean environments underground. There's construction debris, there's sand, there's gravel, there's sub-base roads, there's so much going on. So if you look on the left, this is really how dramatic this is. This is real data. We've real-time sampled the data on the left, and then this is what it used to look like. And I can tell you, if you had a real event on the left of a higher amplitude than that very infinitesimal noise background, you'd see it. Good luck on the right. And this is what it would be in the data. For all those watching that done 2D scans, you know what this is. And you can see clearly down, the hyperbola and the reflected data at the bottom. You can see the noise is gone, and you can see an object much clearer. In some instances now, you're seeing stuff you've never seen before. It's really that important, this leap. And then we get into speed. Anecdotally, like I said, when we go fast, this is actually rapid array data. It's, the systems turn off, so all the channels are red, but it was a screenshot of just collecting data at 40 plus miles an hour. And I wanted to put this in here because I was down in Florida on a demo and had a gentleman who insisted there's no way we can go this fast and get deep. And he understood stacking in these things. And of course, you can't stack as much, but I went out on the same location with a 2D pinpointer system because he had me kind of like, okay, let's go check it out. So I went to the same site, and lo and behold, I saw everything in the 2D system walking along the road that I did in the Raptor. But this particular data I collected in Charleston recently, and this is a gravity sewer way down in the data section where it's over 3 meters, just over 3 meters. So we're about 10 feet down at 40 miles an hour picking this thing out. And I was actually, it was pretty fun to see that go by on the screen. So we get into 3D, they are configured in different ways. Like I said, it's flexible. We have the car mounted system coupled with an RTK system. And then we have the push cart system that can be coupled with an RTK. They also can be coupled with a total station. And that's important because I know a lot of guys are listening, girls, that if you're in the field, one of the most frustrating components of when you run any kind of geophysical device or sensor and there's GPS on it, you go under a tree, you're in a canyon of buildings in downtown LA, you have issues with GPS coverage. So important that we can have a total station coupled to both these the systems. You will not go as fast, and the limitation will be the total station. So, but we can do both. And we actually, when you buy a Raptor array, you get both of these configurations because it's so modular. You can just take the antennas out of the big car mounted one and just put it in the small one. So I did want to put this in here and just say we have tested to 80 miles an hour. I have not. But in Sweden, my colleagues in Sweden have done quite a bit of testing, and it absolutely holds. Its capability up to 80 miles an hour at 5 centimeter spacing. And actually, I mean, you qualify that because that's very small. It's something we use. That's kind of the standard we use when we're collecting data. So when we get into data collection, this is just a screenshot. We have to know where we're going and where we've been. So we have an onboard moving map, and it paints your swaths. I mean, it's kind of zoomed out, so I just kind of show more of the streets, but you'll zoom that in quite a bit more. And you'll just drive around. You'll literally drive with the flow of traffic. Yes, your vehicle should be equipped with lighting and so forth. Everybody should be aware of their own traffic safety and rules and so forth. But if you're going with the flow of traffic, it's important I like to have a light on and so forth. But you got to know where you've been and where you're going. So you have to have a navigation system on board. And this is an active navigation system. You can switch back and forth between watching the data go by. That's only good for the first one because then you really need to know where you're going. And I'm kind of get excited about data, so it drives me crazy that I have to watch the track when I'm driving and not look at data. That's just one of those things. So I want to start I'm going to do a little short video about just kind of shows you from when you get started through the process. It's just kind of a exciting video to watch, just of the Raptor array in action. I don't know, there's a little bit of music there. I don't know if y'all can hear it. That's not as relevant, but what we're basically illustrating is that we can keep up with the flow of traffic. It's easy to put on. I actually put this thing on quite a bit by myself. It fits in the back of an SUV. This is your RTK setup. So it's really not much to it. This is about maybe 15 minutes of work. I'll make a few more comments in a second. Just a good close-up of the map. Okay, so a couple comments on the data collection. The battery on that is a deep cycle marine battery. It lasts about 6 hours. I always carry 2. Power is important, but it really does last 6 hours, which is quite amazing. And that time sequence was basically representing from the time you set it up, and that's about a half mile of 4-lane data collection to the time we're demoving. So it may sound unreal that you can do that in 35 minutes, but you can. And what I want to emphasize too, I've got a lot of experience pilot studying this thing in real life out in California, particularly with the company Gel Solutions. That was the initial pilot company we chose to work with this. And another company, David Evans Associates, was very instrumental in helping us along with that. But we did do a lot of our work. You still want to do a lot of, I don't care what array you use, you want to do your work off peak. A lot of times we'll do it after 8 o'clock, especially in California and LA basin somewhere. And the reason is not because of the radar array, it's because your stress level goes way down. So you can be more productive. So even though we can keep up with the flow of traffic, I can assure you it's a lot easier to do this thing at 4 o'clock in the morning before rush hour than it is otherwise. But let's get into what the real goal is here. So we know we can collect the data fast. And what we really, really found was the big, let's say, bottleneck encumbrance to really being efficient with these systems with software. So we made a big effort, big push to develop our own software that was intuitive. And the goals were here, and that stated here. We wanted the SUE industry to use Raptor arrays. We didn't want just some rocket scientist in the corner of the office be the sole person that could go ahead and do this. So our goal was to make the software very easy to use and efficient. And I like to think that any geomatics expert, professional engineer, someone with a professional education, geologist, or whatever, non-geophysicist, should be able to use this software. That was our goal, and I think we achieved it. And the bottom line is when you get in the bidding process and you're looking at scoping work, if you're the company that has this great solution and your orders of magnitude higher in cost, you may not get the job. So in order to get this to fit in to be more mainstream, this is where one of the big bottlenecks was with software. So I'm going to go ahead and just run this. We're going to run through, this is real life. I'm going to run through, this is recorded, by the way. I want to make sure everybody knows that, because I didn't want to blow up something and do something wrong and type something in wrong or whatever. But this is not rehearsed. I mean, I can do this on the fly, but I wanted to do this. And it's recorded. But there's no edits, no nothing. But this is about a third of a mile of data we're going to put into the system. This is how you get the data in. We try to make everything as graphical as possible because it's easy. And so what we're going to do here, this is my swaths, and these are all my GPS points. We're going to zoom in here. I got a lot of times, you can use the space bar to start and stop profiles, and I zone out sometimes, or somebody that zones out. So we have some errant stuff, but we can just select this stuff. We can delete it because you're not going to really process that. And what you're looking at actually is a contour map in color of how many points per meter we were for the GPS. And the green shows that we're well within, you can set the tolerances on this, and that we're well within, points per meter that we wanted. And then we also have traces per meter. This color representation shows that the encoder is actually at least at 5 centimeters trace interval, and blue is actually beyond. So we didn't hit red, so we didn't undersample. So next thing we're going to do is treat the data. I like to use this DWAL versus DC remove. This is kind of a standard processing routine to remove any what we call drift in the analog signal as it comes through the ADC. To digitize, it causes what we call wow in the data, pretty standard. And I think anybody listening that's ever used GPR knows we bandpass. And these defaults are great because we use the same antenna all the time on the 450 Raptor. So we'll go ahead and pre-treat this a little bit and bandpass it. And then what we want to do here, this is just a simple step. We have some real high amplitude stuff, and it's always nice to tone down the amplitude so when we get back into gaining and working with the data, we don't have this huge amplitude event that we have to deal with that would be, let's say, overgained. Let's say you went over a manhole or something, you're looking at the surface, you'll have this massive overgain or a very shallow metal pipe. So we can control, I don't want to use the term muting, but we can control the amplitudes here, and then we can build them back up in the processing. So we pull this in, and we're looking at our swaths. Now we're looking at raw data, and everything's scroll and whatnot. So I'm scrolling my mouse up and down with the depth, so I can go right down, up and down. There's a manhole right there underneath the hand. And you're starting to see trench features beautifully in the near surface. The other thing you can do too, color palettes. Everybody has their favorite. You can go ahead on the fly, build a color palette that you like. I love this one. I can save it. I just wanted to run this, not save, so you can see how easy it is to go ahead and just build a palette. And when we get the interpretation. So this is just a screen contrast. It's not really a gain. We call it a linear gain, screen contrast. So now we're starting to look at the data, and then we can start to see some things that are features that are utilities. There's a very big transmission line sitting right over this spot. and I noticed the GPS was off, and I love this feature because you can come in here and you get a little bit of disturbance in GPS, and you don't want to adjust that or delete those points without data. So what we can do is, if you know the alignment of this utility and you're confident of it, you can actually just move the GPS points, and you can take the error and drift out on these, these perturbances that you might get localized. Before the data comes in, we can remove float points and so forth. But I'm running through this to give you an idea of, just how quick we can run through the data and analyze it and get it to actually a CAD export, at least the line data. So we've got the geometry set. We're going to go back here, and we can take a look at the data here and a little closer view. And what you're going to see now is that myself or the driver at the time, we didn't overlap the swaths. There's a little bit of a gap. We're starting to see lots of utilities. That's about a meter down, by the way, if you look lower right. But we're going to do a couple of things here now, the data, a little bit more massaging the data, some standard stuff. Amplitude correction is just a fancy word for gain. So there's an AGC, there's a spherical divergence, which is basically kind of a spherical exponential gain. I like the AGC. And this ring down removal feature is basically there for really superconductive soil like you might get in Denver, and sometimes we get a lot of ringing in array data. So we're going to go ahead and process this out. There wasn't really any ringing in this data, but I just wanted to show that we have it. So now it's starting to look a little better. Very obvious that there's utilities here, and what you're looking to do is the top view we're slicing down, and those are still in hyperbolic representation. But I want to get that line out. We're going to do an interpolation throughout the whole data set. And this is a lot of math, so it's going to take about 30 seconds on this data set, but so it'll feel like forever for me. But we're going to go ahead and close all the gaps and smooth out the data. It's not going to move anything. So if there's a pipe in a certain location, it's not going to move anything. It's just going to fill in some of the gaps. So we have a nice complete data set. And while thinking about it and processing time, people may ask, well, are you on a mainframe? What are you doing here, man? Are you in a lab coat doing this right now? No. This is basically a laptop. Any laptop that's going to be able to handle CAD is doing this right now, because it's exactly how this computer was spec'd. So we've got our interpolated data. We can pan through and just like poke around and look around. There's a lot in here. We're not obviously going to do everything we can do with these data today, but I'm going to just give you an example of how we can fly through the processing and start to analyze the data. So next step is now we're going to get into what we call migration. This is where we're going to take a hyperbola, and you'll see this in real time. We're going to take what we call a cut line, and we're going to cut through the data. We can do this anywhere, and we're going to look at what the 2D profile looked like. And the beautiful thing about this is what you're used to looking at, but we don't want to look at hyperbolas now. We want to collapse these, so we can on the fly do a migration of these data. You can under or over migrate. Under, you still have a hyperbola. Over, you'll get like this parabolic, so you don't want to go too crazy. So we're going to collapse these on the fly, and we're going to set the velocity here. And I want to talk through this because what's beautiful about the way we set this up, one velocity doesn't fit all in the ground, and a lot of people may notice that in 2D radar, that we can migrate this at this velocity, but the deeper we go, that could change. Laterally, that can change. So when I migrate this, and I'm not going to do it now because we don't have limited time, but I can do up 3-4 migrations on this. I can go down deep and look at a pipe and say, well, this velocity is not quite right. And I can use that as a velocity in different sections on the data. So here we are, we've got data. Now we're starting to look at utilities as pipes. And the next phase now for anybody looking at the data is like, I need to get these data out. And we can do this as lines. We can put points in and different features. If there's a fault, we can put points. But we did put descriptions of the utilities in here, and everybody that's listening is familiar with how this works. You may not know what these are, and particularly if you're just processing data, you may not know that these are a water line, a gas line, or sewer. The only way you could ever imagine that at this phase is to have these data tied in with other information, manhole that's been surveyed in, and you know from notes and field notes, hey, this thing it's a gravity sewer. This is a water line. But we put them in there knowing that wouldn't always be the case. But what's really great is you can actually customize that any way you want. You can call these unknowns. You can put your name on them and say this is Jim's line or Matt's line or whatever. It doesn't matter, but most people would just put it as unknown. You can define the colors. You have complete flexibility on this. So I'm just going to do a couple representative picks. One thing I want to say is these picks, I'm going to do a couple now just to accelerate it, not doing cut lines, just to put some more data in. These picks, you wouldn't be going this fast. You would be very careful about where you picked. You'd put a cut line in and pick the top of the pipe. You can do it orthogonally off hyperbola, but within an hour, there's a lot in this data, so there'd be a lot that we could work with. And I didn't want to use, and I have a choice on this too for the webinar. I have Florida data, it's perfect. And I like these data because it has the tremendous velocity variation. There's a lot here. And I wanted this to look real. And I'm considering this data to be a middle of the round, let's say middle of the road data set, no pun intended, of decent soil, but not Florida sand and not horrendous San Antonio clay, which would not be good. So just to give you an example of how you can pick these lines, I'm just getting enough data out, lines so we can show the extraction of it. Very simple. And this is where we wanted to save time for the to get the line data out. So I think we're doing one more here. Let's do one more. I guess people can't follow. I know a lot of people know GPR, but we're just looking along the strike of the pipe through that cut line. So we're looking at, instead of a hyperbola or orthogonal, like a point, we're looking at as a pipe. So we've got some data, we've got lines. We can turn everything on and off so it doesn't clutter the data. We can go in, and this is what's beautiful. You can move things, you can delete. Like I said, you wouldn't be going this fast. We could do different migrations at different depths. Just a lot of stuff in this data. Not sure what this is. I think I thought it was the gas line going across because somewhere along the road there was a marked gas line, transmission line, but it's way too shallow. So we'll call it a gas line. So assuming you work through this data, I would imagine this data set in the interpretation phase and extraction right now and getting your migration velocities. I would probably spend a couple hours on these data and really pour through it. I'd probably have supporting information, but I just wanted to show you the workflow. So now we can just, all these data lines that you pulled, we can just extract these as DXF. And then we can just go, I just want to show you real quick, I have a CAD viewer. We just going to jump on CAD. Yeah, and there's nothing here. I'm not a surveyor and I don't have a base topo, but when these data would come in to a base topo that the SUE firm would obviously have rigorously surveyed. And these data would come in, and there's a whole bunch of workflow that would happen here, adjusting elevations to the radar data. There will be EM supporting information, quality level D, and all kinds of stuff there to be concerned with. So I just wanted to give it just a quick overview of how these data can be fairly quickly processed or very quickly processed and put into line data to get into CAD. And that was like I said, that was one of the goals. Let's make this thing as simple to use as you possibly can, and let a lot of people be able to process data. Obviously educated people that care and want to spend the time on it and can be trained properly. So anyway, we get in to 38. we've got these tools now. They're getting more mainstream, easier to use. So we all know 38.2 has been the standard since 2000 for 2D SU. But I talked to James Anspach, which many, many people listening know. He's a great guy. He was the founder basically of the SU process. I spoke to him a week or so ago, and he just gave me some bullets to get everybody a little bit of an update real time. The 3D standard's coming out December 2020. As far as Jim's concerned or knows, it shouldn't have any issues. It's in committee. Some of the new things are in bold. In addition, obviously, to 3D, there'll be a utility report that will be required with the utility drawing. And I don't know, and I'm sure in that there'll be samples of utility reports and what they would expect to be in a report. So instead of just, a lot of people wouldn't pass, but just hand out maybe a spreadsheet with the contacts they made, for example, for quality level D and these kind of things, and maybe just a drawing. What will be required in the future will be a written report, which may explain certain things and aspects unique to that project and that might be of concern. So there'll be quality levels are going to be prescriptive. And I forgot to call Jim when I rewrote this and ask him what he meant. And if he wants to type in, Matt, it means this, we can take a look at that because he said he would be listening. But of course, for 3D, you're going to need depth. And you're going to have depth as an attribute from records. And of course, geophysics is what we did with an array that includes radar. It also includes EM. A lot of people don't realize and don't think of electromagnetic locators as geophysical tools, but they are. And all the other things that you would use. It's going to include vault dimensions, which is great for radar tomography because we're pretty darn good at getting the outside dimension of those vaults when we do the imaging. But you will have to pop a manhole, probably get permission, either laser scan or do something to get the inside vault dimensions. And a lot of companies do this now that I'm familiar with. They'll do a little bit of, they'll have aerial utility work documented. And of course, the appurtenances that are along the street, hydrants and so forth, poles, clean outs, whatever, handholds. These things are fairly much or pretty much already put in there. And then there's a lot of descriptions. And then we're using the term uncertainty a lot more. And I think it's a great way to describe the data and the level of uncertainty because the least amount of uncertainty for anything would obviously be quality level A exposing something. And then when you think about it, that's still not 100% certain because you could have exposed the wrong utility. So there's a lot of emphasis on uncertainty in these deliverables. So we have these arrays, they're fast, it's demonstrably easier to use than they ever were. You just saw the software, there's nothing about that software that is not how it works every single time you boot it up. The data can be extracted very easily and they're great for large corridor projects. They're accurate, the RTK systems are very good. The RTK systems can have accuracy, sub-centimeter, but when you're running the array, you're not going to get that. It's just a fact. When you're driving, that even that array data is going to be within probably 10, 20 centimeters. It's not going to be at the tolerances of the RTK. It's just impossible. And one of the beautiful things with all these sensor data, you get into arrays and this high amount of data that's of good quality, you're actually at the end of the day reducing the amount of test holes that you'll have to do, which actually reduces project costs in the end. It gives the engineers and design people a much better understanding of where your conflicts are in your design so you can go ahead and focus on those areas. So the bottom line is we get into Raptor systems and the software that's very streamlined where you're in a bid process going, hey, I got this great tool, but I'm 25, 30% higher than the other person. And sometimes, and everybody listening that is involved in this business knows there's a bunch of people out there and they look at just a dollar value and they say, okay. And it's not quality-based bidding sometimes. So if you can get those two deliverables to converge in terms of cost, then you've really done something. I just want to put a plug in. There's a book from ASCE. It's really about the 2D standard for 38, but it's just a great book. I picked up a copy at the last seminar I was helping teach with Jim and some other folks. It's just a great read, and it's really something you give to your clients. And it's, I just wanted to mention this because I wouldn't have plugged it if I hadn't realized that it's just a really nice overview. It's not, you can read the standard, but that's not what this book is. It's a little bit more in depth. It actually does talk about uncertainty and some other things. Really good read for your clients, for example. I just want to kind of wrap this up because, I've been in this industry a long time, particularly the radar industry, but I've also run a vacuum excavator, and I've done 2D EM. I've done 2D radar. I'm not a surveyor, so I'm not really qualified to speak to that, but I've worked with a lot of surveyors. But, if you're going to go ahead and have a deliverable, pursue, or any deliverable, we're at the point now, it is all in, and I think everybody gets that now. Years ago, it wasn't the case. There were people actually that espoused one or the other back in the day, and it was a disservice to the clientele and a lot of people, actually. So it's just to keep in mind that you're never going to solve everything with the array. I like to emphasize that, but man, you can get a lot of information that you never had before. So I just want to close out also. We're an established company, 5 years. We've got a great team out there now globally. This is the folks I work with. They're all great people. I also want to mention that Tracer Electronics, Lebanon, Tennessee, they're A players just like everybody else, but they go to the next level. In fact, they're excellent at repair. So all of our equipment in the United States, and that would include Latin America if they choose, can come to Tracer Electronics in Lebanon, Tennessee. And they have an amazing team there. Worked with them already for quite a while, and very impressive facility. And there's not anything they can't fix. And they also fix their Vivex Metrotech reseller, as most of these folks are here, and it's a couple of RD guys in here. But they can fix all EM locators and calibration stuff. And also, I just want to plug the MLID GPS systems. We are testing them, and we have used them. I will not tell you the cost on it, but I can tell you it's one of the lowest cost RTK GPS systems you'll ever get your hands on. Pretty amazing. Runs off Android like all our stuff, so we love it. And it's the simplest system to use I've ever used. It doesn't have 10,000 buttons on the TC3 controller or whatever that thing is from the other guys. Very user-friendly, and I really like it. I just want to say thank you. I tried to keep this as short and as concise as possible. I hope I achieved that. I don't know how much time we have left. I think we've done well. So I think at this point, Geraldine, you are going to maybe throw some questions at me, but am I supposed to do something on my end? Do you have control?
I will take control back here in just a moment, but we do have one question for you so far.
Okay.
And if anyone has any other questions, go ahead and type them in now. The one question that we have is, what is the width that is captured when driving?
Ooh, the exact width, you caught me. It's like 1 meters. It's basically, if you look at the vehicle, you're looking at basically tire to tire. I mean, it's just inside. So it's, what is it, about 5 feet. So, the way it works too will overlap. This, when you're using the moving map, it's good to have a little overlap because then you don't get those gaps. And we can handle some gaps because interpolation will take care of that. But if you see a gap about half the swath width, you need to go ahead and fill that in. And the beautiful thing is you can just, with the moving map, you just go up and down the road. There's no penalty to overwrite the data, none. So you could go through a narrow gap and resurvey over the same place that you did on, let's say, the outer third of each side of the antenna. There's no penalty for that. It doesn't matter. Just the data will be processed just the same. So let's call it 5.5 feet or something like that.
Okay, we have a couple more that came in. How many antennas are in the array?
There are 18 antennas. Excuse me, sorry, 17 antennas. There's 9 transmitters, 8 receivers.
Okay, and one more question. What is the CAD output? Line, polyline, 3D polyline?
It's DXF, and it is, you know what? I'm not a CAD guy, It's whatever is needed. That's an awful way to answer that question, but we work with CAD people to help us develop it, and it will go into CAD as layers, and it will be, I don't know, I know there's vectors and raster and polylines and stuff. If that person can get back with me, that's
I'll
a
forward
great
you
question.
yeah,
Yeah,
I'll
I can.
forward you the questions and then we can get an
Yeah,
answer.
okay, that's fine. I just know we work with CAD folks to make sure it worked, and they could get it in base drawings. And it works, and it comes in layers by how we define them. So
We have another one that came in. What is the reliability of detection of non-conducting materials?
that's a big question, because the reliability is absolutely determined by what it's in. If you've got a plastic PVC pipe that's 2 inches and it's in a near surface filled with water and it's in sand, I would say the reliability would be extremely high. If you take that same pipe and fill it with air and put it at 10 feet, the reliability let's put water in it, put it at 10 feet, the reliability of detecting it is very low, if not impossible. So there's a whole combination of factors that all GPR, this isn't even just array, have to deal with, and that is range, resolution, and that is dictated by frequency, it's dictated by your soil conditions. So it's a whole host of things. And the best way to describe it is, if you can't see it with a 2D radar, you're not going to see that utility with an array. However, the beautiful thing is, and I didn't put any data examples, I probably should have, but if you go in a place like Denver or somewhere in Texas where the soils are superconductive, it is amazing how beautiful the trench lines will show up on these in the tomography data. And then you go back into uncertainty. So you could still pull that information in. You may outline it as a trench in let's say your CAD drawings, there's a utility trench, but your degree of uncertainty of whether there's utility there or not definitely goes down. You're more certain there's utility there than you were. And you may not even be detectable with EM, because you may not even know that it's there to even look for. And I'd like to always talk about EM versus GPR in the sense that, with EM, you sort of, other than two-man sweeps, which everybody on this call would probably be familiar with, you sort of have to know where the utility is to find it with EM, sort of. And where GPR is a wildcat tool that can just go over any ground. You can pick up trenches, you'll pick up things. The beautiful thing about array data, it really makes the interpretation a lot easier, because any of these folks online, which is probably the bulk of these 2D GPR, knows it can be really tough in some soils to sort out what you're actually looking at, and it takes a little bit of time. I hope that answered the question.
We have a few more that have come in. How do you manage with total station in and amongst traffic where GPS is unavailable?
It's tough. This is where you do off-peak hours. We did a project, I was involved in a project in Spokane, Washington. We did 2 miles, and we were able to do 90% with the GPS, but we had these buildings that just didn't like us, and there was almost like a shadow. So we set the total station up on a curb, and it's line of sight. So we were doing this, I believe it was 2 o'clock in the morning, no traffic, 0 traffic. And we put it up on an intersection. So as we were, if the total station prism is above the vehicle, just above it, you can go both directions. So what we would do is we would track by. And of course, like I said, you can't go as fast, because there are some better total stations now. They're getting faster. Their servos are pretty fast, but still, you're not going to whiz by this thing 50 miles an hour. So you're going to be back to the 10, 15 mile an hour range, and it's line of sight. So you have to set up the total station to see the prism. And so what we did, set it up on an intersection, and we drove by it. It was locked on. It's locked on. A lot of them now are beautiful. They have a video on the controller. You can see where the total station is, and you can lock, and it tells you it's locked. And then you just drive down the road, and you'll know it's locked. And we're painting the swath just like we do with the GPS. And then we stop, and then we turn around, and we do a U-turn. If we were around the block, we'd lose it, so we'd have to reacquire it. But it's going to slow you down, no doubt, but it is a good backup.
And what are the tolerances of accuracy?
Well, we talked about that earlier. You know, when you're using the array and you have an RTK, or a total station would be the most accurate, actually, believe it or not, because of the way it works. But on the RTK GPS, no matter what system you're using of GPS and RTK, if you're standing still with it and you sit there and take a reading as a surveyor would do on a monument or something like that, you're going to be sub-centimeter. But in RTK mode, moving down the road, you're not going to get that. And we center the antenna right over the array, and the offsets are all calculated into where the targets are. But I'd like to say a safe zone is about 20 centimeters. So when you see the data that you saw in the 3D processing, you're going to be somewhere 20 centimeters or less. I don't think it'll be much more unless you go into float, but those are the points that you'll reject. And we have, I didn't mention this, but we can clean up the GPS data in Condor more. You know, we can delete the point. You saw me delete a whole bunch of swash. You can delete, if you brought in RTK5 float points that were kind of erratic, you can just delete them. You could move them, but you're not sure where they should go, right? So you can delete them. But we have that on the talent acquisition software. We have a utility program, and you can just check off, I want to reject any float points, DGPS, whatever. And then that data will go out into a final folder for the project. We call it a combined file with all the, you know, the erroneous GPS points not even in it. So you're not even dealing with it downstream in Condor. Very efficient.
I think we have time for one more question here. It's actually a two-part question. Are there companies currently using ImpulseRadar throughout the country? And is it common for them to supply the raw data of a prescribed area to a SU engineer that he or she has and uses the software to process and create SU documents?
I'm not sure I understood the question, but yes, we have Raptor systems. There's 3 Raptor systems in the United States right now active, and that is growing now. I've got quite a few commitments coming up this year. I didn't understand the second part of the question, though, about the data processing.
I can forward that to you.
If you want to reread it real quick, maybe I can grab it for
Sure.
the person.
Is it common for them to supply the raw data of a prescribed area to a SU engineer that he or she has and use the software to process and create SU documents?
I'm not sure I understand that question.
Okay.
I really don't.
I can forward you the question.
I don't know if they're
and the
saying
email.
that we're not a service provider, so I don't know if they're thinking we'll go out and collect the data and just hand it off raw to somebody else. We're a manufacturer, so we're not a data collection company. So yeah, that'll be one. If I can get the person's contact information, I'll just give them a call and say I'm not quite sure. But to be clear, we're a manufacturer. We can set you up with a radar system and the software, train your personnel, whoever that may be, to use it, and you will do your own interpretation and data collection, et cetera, for your deliverable.
All right. You have a few more questions. I will forward those to you along with the email. Thank you, Matthew, for your presentation today. We appreciate you taking the time to share this information with us. And everyone who's participated in today's webinar will receive a survey link. If you please take the time to provide us with some feedback on today's presentation. And then to learn about more educational opportunities, you can visit dp-pro.com. Thank you, everyone. We hope you have a great day and stay safe.
Thank you, Geraldine. Thank you all for participating, and stay safe.
Thank you.
Bye.